distant sun. These distances are set by the details of the Earth. Let me say this in a different way. If the Earth had a different blend of gases, these might be really small wheels. If we didn't have water, we most likely wouldn't have these at all. Because of the gases on Earth, it just so happens that we can fit 6 wheels from the North Pole to the South Pole. But that's just because the baby Jesus said so. On Earth it's 6 because of the gases we've got. Different atmosphere on a different planet with a different distance to the sun could have 2, 4, 8, 12, who knows. It just so happens that the Earth has 6 and you have to know that. Something else you have to know is their names. Please look up. They're called the polar, temperate, and tropical. Southern tropical, southern temperate, southern polar, northern temperate, northern tropical. And these 2 are named after the people who discovered them, the Farrell and the Hadley cells. You have to know those names. Second of all, you have to know their size. 0 to 30, 30 to 60, 60 to 90. They're all the same, 30 degrees of latitude. And now the tricky part, you've got to know which way they spin. But you can always understand which way they spin if you know one fact. Please look up. The most heat on Earth is at the equator because the equator receives 12 hours of sunlight every day. Because our equator gets 12 hours of sunlight every day, that's why we call it the equator. It is equal. The equator is the main driving force to get these wheels spinning. Now, have you heard of this thing called friction or drag? Molecules rubbing up against each other want to stick together. They're tacky. So now watch this. If I spin my left hand to your clockwise, to your right clockwise, and it's in contact with my other hand, you'll notice that I make opposing directions. Watch. Because of the drag, they spin in opposite directions. Does that make sense to everyone? So now, where the equator has a lot of rising air, north of the equator it spins that way, but south of the equator the opposite way. Everybody see that? And then wherever they touch against each other, they will power themselves in opposing directions because of drag. So look up, please. At the equator, you've got the most heat. So that spins this one, which spins this in the opposite direction, which spins this in the opposite direction. If we go to the north, please look up. This one spins like this. So the next one spins in the opposite direction. So the next one spins in the opposite direction. Does that make sense to everyone?
Does that mean that it gets like weaker or slower as you go north or south, like the polar ones?
No, because there's a combating influence. You're right that the force would be lost, but don't forget that the donut around the equator is much longer than the donut around the North Pole. It's a sphere. So you're right that this force would not be sufficient to power this at the same speed if they were in a cylinder Earth. But because they're in a spherical Earth, there's technically a lot more molecules here to power just a few in a smaller donut, to power just a few in an even smaller donut. Does that make sense? I want to check in that everybody knows the 6 cells, their names, and now which direction they spin. So check this out. Where do we have hot air rising from the surface to the upper atmosphere? The equator and the 60s. And where do we have cool, dry air falling out of the atmosphere? The 30s and the poles. Like that. Equator is wet, 30s are desert, 60s are wet, and the driest deserts on Earth are the North and South Pole.
Goddamn.
The funny thing is, months ago, I talked about that pattern of biomes, and I said later in the year I'll explain to you why that happens. This is the explanation of our biomes. Technically, the atmosphere has less water above the equator and above the poles because that water was shed as the air rose in the first place over the 60s and over the zero.
Why aren't the clouds carried to the dry spots?
Well,
What's up with like Central America, like the Yucatan? It looks like it's kind of on like the 30s, but
it's cheap because it's surrounded by water. So we talked about those little flukes.
it gets a little moisture from the other one.
That's basically marine layer rain, not high altitude rain. Why don't the clouds get dragged?
Yeah.
Because clouds are an ephemeral moment. The cloud, as we know it, is that rare interface between gas going into solid or liquid. And that happens at this exact tipping point, where the water's lost just enough energy to start clinging to its fellow molecules and start making a different substance, no longer a gas. That tends to happen the most driven by the cooling of hot air. Hot air rises, and as it rises, it cools and condenses. Other forces can create rainfall elsewhere. We know that, for example, the desert has rain. But it's not this big rain. It is secondary forces at ground level.
Well, I mean, like, when the water's carried up, why isn't it carried across by the wind created by the...
Oh, because it doesn't have enough air. So it doesn't have enough energy. So in exiting the heat source, its energy content starts to dissipate. If you could get a hotter planet, this would mushroom a little bit. Does that make sense? So we got 4 rules. We explained 1 circulation cell. Now we've explained 6 circulation cells, the pattern of wet and dry, and their rotation plus names.
Is the diagram that we did of the convection cells for like a 30-degree one?
You mean from 0 to 30 or 30 to 60? I would call this equator to 30 degrees north. And you could also just pretend that you're looking at it from the opposite side, and now it's equator to 30 degrees south as well. Where it rises, that on our planet is either 0 or 60. Where it falls on our planet, it's either 30 or the poles. What else?
So on that, the axis of the Earth.
Yeah, right. So I tipped this sideways to explain this one, just so that we could see this from ground level. Yeah.
At night, is this just fueled by like the Earth gradually cooling and getting that heat, or does it change?
First of all, at night these slow down because you've lost your driver of energy. At night you get a lot less rain, for example, because you've got a lot less movement of air, so you've got a lot less transfer of energy, so you've got a lot less condensation of precipitation. At night, this might be fueled by plain old drag. Like somewhere else, there's enough movement that this movement is being applied to where your nighttime sky is. But I think it's a safe trend to assume that the speed of a convection cell, or the force of a convection cell, is proportional to the amount of energy being added by the sunlight, and thus highest at 1:30 in the afternoon and lowest in the morning.
So just by that, this could also like be be lessened in like the North Pole winter, even with like long periods of less sun.
Funny thing is that the drag is, the teeth are still grinding. So the equator always has movement without seasons. So the equator is still driving the other six despite their seasonality. But yeah, you're right. They probably do get some tweaking about how much energy content is actually at play because of season. Anybody else? Okay. The last thing I want to do is imagine we are this little dude right there at 15 degrees north. Okay? I'm going to draw that dude at 15 degrees north right here. And that dude at 15 degrees north, because he's on the ground, which direction does the wind move? From south to north or north to south?
North to south.
You can see right here, which way is the wind moving for this fellow?
North to south.
North to south, right?
Yeah.
You can see the air coming from the north past him to the south where it rises and then goes north at a higher elevation. Do we agree?
Yes.
So, first of all, we're going to have wind from north to south at 30 to the equator. And you can also see, I've said a lot today. And by the way, you can also see from 30 to 60, it goes this way. And then again, from 90 to 60, it goes north to south. Do we agree with my wind directions?
Yes.
But which way does the Earth rotate?
To the right.
To the left or to the right? The Earth rotates that way. So because the sun is fixed, they see the sunrise first, then as we move toward it, we see the sunrise last. Does that make sense to everyone?
Yes.
So can we agree that the Earth is rotating?
Yes.
Yes? Rotating? Gabe, you need me or just chilling? So rotation goes this way. Oops. There we go. From the west to the east. Now, I'd like to do one of my favorite demonstrations of the year. What happens when we add surface wind to Earth's rotation? I will be the wind, but I need someone to be the rotation. Please volunteer. No, right here. Okay. Ken is our trusty volunteer all year. I love it. Thank you for volunteering, Daniel. All right. So that we don't obscure the clutter on the whiteboard, I'm going to ask you to rotate the Earth right here. Okay? All right. And so you're going to hold it on this side and pull it that way, but I'll stand on your current left. All right. Yep. Now, yeah, we're going to go kind of slowly so that I can apply wind. So he's applying rotation to the Earth underneath our feet, while I will be applying surface wind. First, I'll show you what I would do if his paper weren't there. I'm just going to go like this. Because we've already agreed that the wind goes from north to south, haven't we?
Mm-hmm.
Yes. And then Homeboy's going to go from the west to the east, because again, we've agreed that that is the way that the Earth is rotating, yes? Okay. So, I am starting at 30 degrees north. The bottom of the paper is the equator. And when I say go, Daniel will begin to rotate the Earth while I begin to apply wind. Agreed? Ready, set, go. Now you can see that I went in a direct line top to bottom, right? I did no funny shenanigans. I did not play any mean tricks. I started here and finished there, going from north to south. Like we agreed, the wind blows between 30 and 0 north, right? Yep. Thank you, Daniel. You can go back to your seat. Because I really want everyone to be able to see this. This single line contains so much meaning for me, as a South American in particular. This is what you get when you apply the circulation of the Hadley cells to the Earth's rotation.